magnets have two poles, north and south. If I see any of you write anything about magnets being positive and negative, I'm going to be very upset. Magnets are generally neutral. North and south is what's going to give them the magnetic properties. Unlike poles attract one another, you know that, same business as well, of course, I mean, same business as we did with electricity. And like poles repel one another. So basically opposites attract, likes repel. And magnetized objects, either pole, attract some non-magnetized objects. Still see the screen okay? Mm-hmm. Alright, so over here, what do we call this? What type of magnetism was this when we said some magnetized objects attract some non-magnetized?
Paramagnetic.
There you go. Yeah, your paramagnetism. A little extra credit over there. If you feel like looking these up, ferro, para, and diamagnetism, don't expect to develop a rich understanding of those magnetisms just from what you find on the internet. They're largely based on quantum mechanics, and it's going to be a little time before you fully understand that, if you pursue physics. Okay, so magnetic force, attract or repel, this is pretty easy. North and south, attract, south and south, repel, north and north, repel. That's basics right there. Let me ask you a follow-up question though. Of course you see here that the north and the south will attract. But this is south pole and this is also a south pole. So is there any interaction between them? They repel. They should repel, right? So there is a repulsion here between this south and this south. And is there also a repulsion then between this north and this north? Alright, so who wins? The attraction or the repulsion?
Attraction.
It does, but why?
Closer.
Yeah, it's about the proximity. Now you practiced this, was it yesterday or the day before, with the magnets, you were playing with them. You noticed that the closer they were, the stronger the force felt. So, it has to do with the proximity. Alright, if you break a magnet, can you get just a north or a south pole?
No.
Nope. No. Good. Next page. Alright, you notice up here, how do we determine magnetic field direction? You notice that most of this chart is filled in. What that means for you is, in this course, you're not going to be asked to calculate any of this business. Magnetic field strength goes by the letter B. They won't ask you about that. The unit is the Tesla. They won't ask you about that. There are plenty of equations. If you do SAT 2, you have to know them, and in AP you'll learn them. And they're not in our reference table. However, you do have to know all fields are as a vector or scalar. Hello? Vectors. You draw them with arrows, vector. Vector fields. So, it is a vector. You do have to know that. And here's our friend. We had posi before. Now we have northy. Look at northy. Maybe. Alright, so northy is our north test charge. Basically, you put northy anywhere outside a magnet and it'll show you where the magnetic field is pointing. Poetic again, like we did before. Wherever northy goes, so goes the magnetic field. Remember that? Wherever posi goes, so went the electric field. So wherever northy goes, so goes the magnetic field. Really, we could do the same thing for gravity and call it massy, I guess. Alright, translation. Magnetic field points away from north poles and towards south poles. I'll clarify this now. It doesn't really come up in this course, but this is outside a magnet. So in case you ever go on, you'll have that little clarification. Okay. Now, a compass is a fairly simple device. Everyone know what a compass is? I mean, I know you've seen them. You've probably dealt with them.
Magnetic field of the Earth.
Well, it could do the magnetic field really around anything. Yeah. But a compass itself, physically, that little strip in there is just a magnet. So it's a magnet immersed in some sort of fluid that allows it to move freely. So a compass is a small magnet, and its north end is marked. So a compass, just like a little bar magnet, and the north end is usually marked here. This one it's red with a white dot on it. Sometimes they put an N on it. A compass is basically a practical version of northy. When you guys think of posi, do you imagine something kind of like a proton? Not that you can see a proton, but I kind of think of like a little positive proton. Northy is kind of like a little baby compass. That's all. So here's the note, and take this note seriously. The direction that northy moves, that the magnetic field lines point, and that a compass points are all the same, north to south. So they'll all do the same thing. And the reason you have to know this is they might ask about one, or give you one and ask about the other. They might give you the magnetic field lines and ask you which way does a compass point. Or they'll give you a magnet and they'll ask you which way a compass points. And you'll think about northy. Maybe they'll give you a compass and ask you about the direction of the magnetic field lines. They're all the same. We're going to do that twice on the next two questions. So here we have two questions. First one shows you the direction of the magnetic field lines near point P. So you put a compass at point P. Which way will the needle point? Think about that for a second. So we place a compass right here. And this is one, actually, the first time you do it, you could easily get tricked. What do you think? What do you guys think?
Same direction.
Yeah, it's 2. So sometimes you get thinking about, wait a minute, this is pointing away from north and this, that. Don't get too complicated with this. A compass, the field lines, and northy. They all point the same way. In fact, this compass, no matter how it looked over here, it may have been pointing off to the side or some other business. As soon as you bring it into that magnetic field, it will move and it will point along with it. This is actually telling you this is the north end of the compass. And in fact, there's probably some sort of north over here and some sort of south over here. So it will be choice 2. Here, we're going to sketch the field lines around this compass. Let's assume that this is the north end of the compass. So how will the field lines look? Derek, what do you think?
Wait, which one? Which arrows the north?
The darker I made the north.
They'll point.
Yeah, they'll point down this way. You know, right here, it's something like this. Now, this could be curved, straight. We'll make it simple. We'll say the field points something like this. Okay? So the letters on the compass, the northeast, southwest, that's not telling you anything. Sometimes people pick up a compass and they're like, oh, well, the N is, the north is this way, the east is... You actually have to look at which way the magnet itself points. That's why the dial spins. You align it so the north lines up with that, and then you can get an idea of east and west and all the rest of that. Just beware, if you're ever near a magnet, it's going to change it. Near anything magnetic, this cannot be trusted. Usually out in the middle of the woods, as long as your compass is alright, you're not carrying any strong magnets, these are relatively trustworthy. But I would not leave my house with a compass that was just sitting in a drawer somewhere and trust it. Okay. Now, this gets at, actually before we even do this, this is a little interesting. This gets at something. Maybe this can bother you. Has anyone bothered yet by the whole business about the compass pointing north? Redraw over here, redraw. You know what this is?
Earth, but it points
Earth.
to
Now,
the
Earth.
magnetic north, not true north.
Oh, look at this guy. Earth basically behaves as if it has a big bar magnet in it. There's not a big bar magnet in it, but it behaves like there is. So, let's say the equator's here. Here's the northern hemisphere. Here's the southern hemisphere. Here's what we call the North Pole. Here's what we call the South Pole. And if you were standing here in New York, and you took your compass out, which way would it point?
Towards the north pole.
It would point up over here, right? But I just told you that the compass literally is a magnet with its north end marked. Does that make sense?
Then the geographic North Pole is close to the magnetic South Pole.
Good thing we got it even here, right?
Wait, what?
By itself, does this, won't worry, we'll talk about it more. Does this make sense?
No.
Should the north end of the magnet point to a north pole?
No.
Oh no.
No, it shouldn't. But here's part of the disconnect. There's two reasons. One, people who are mapping the Earth originally are not necessarily the same people who originally were figuring out magnetism. In fact, of course, they were different because it happened at different times. This is what we call, Dave said it, this is the geographic North Pole. So you work with latitude and longitude and a big map of the Earth, and you have what's geographically called the North and South Pole. What we've come to learn is that the magnetic North and South Pole actually at the present time don't line up with the geographic North and South Pole. They actually line up with reversed. This is a magnetic, we'll put a little B for magnetic, North Pole, and this is the magnetic South Pole. So in fact, they're flipped. So the two are not the same, and if you were ever having a conversation with someone about magnetism and geography at the same time, you'd have to clarify. They're not the same. And this is an interesting thing, you learned about this in earth science. You might say, well, is anyone bothered by this? We should just fix it, right?
Yeah.
Let's just change the names, right?
Yeah.
That actually wouldn't work. That wouldn't work forever.
There he is.
Do you remember in earth science?
It'll switch eventually.
Yes. Do you remember this? Maybe you saw a diagram like this in earth science. They had the Mid-Atlantic Ridge. Remember learning about that?
No.
Yeah.
That spot in the middle of the Atlantic Ocean between the Americas and Africa, and the two continental plates are diverging. The two tectonic plates are diverging. A new land is being created here.
No.
Well, what's happening as that new land, you get the magma comes up and then it cools, touches the water, and you get new rock. As it forms, the rock there actually aligns. There are minerals that will align with the magnetic field of the Earth. You remember this?
Wait, like, doesn't it switch?
Yes.
Pull it.
So what they do is they look. They say, okay, I'm going to go 100 miles this way, 100 miles this way. What they find is there's a strip where everything seems to be aligned like this. It's all aligned the same way. And then you go another 100 miles, and you find a strip that's aligned the other way. And you find things in between. So what this is indicating is that actually this magnetism of the Earth is switching. It's reversing. And this happens every so often. And the true effect of this makes some people very nervous because we're not really 100% sure what the true effect is. In fact, the magnetic field will look like, it looks approximately like this around the Earth. It goes out from the north, loops around, comes into the south. Out from the north, loops around, comes into the south. And this is an extremely important thing because not that far off in space we get this big thing called the sun.
Oh no.
Oh yeah.
Oh
No.
no. Oh, it's a Jake.
No.
Oh, it's a Jake. It's
I have no idea where he is. He has not been here at all. Bye. You know where he is?
Nah,
Don't
I'm
tell
probably
me.
sick right now.
Alright, so the
Nice.
sun spits out lots and lots of high energy particles. A lot of them are in the form of high energy protons. So high energy charged particles. So if you have charged particles that are moving, are they affected by a magnetic field?
Yep.
Yes or no?
Yes.
Wake up. Charged particles moving. You. That's why when we turn this on, there are charged particles moving and the compass is deflected. We had charged particles moving and it got deflected. Yes, it has an effect. You know what happens when they come over here by our magnetic field? The field actually deflects them around the Earth, and some of them get funneled down into the poles. That actually gives you the effect called an aurora. I've never seen an aurora in person, but I feel like that's the sort of thing you have to do before you die.
I saw the North Poles.
Oh, it's
You can see it in northern New York.
So that's what I've heard.
I saw it in Buffalo.
Is it something you need to do before you die?
Yeah, it's pretty. It's not like it's above
can think
you.
of
It
5
looks like
things
you
you need
see
to
it
do
like
before you
2 or
die.
3 miles away.
Yeah.
That's what it looks like.
That's pretty cool.
all
That's
mad
That'd be
fun.
pretty
I
cool.
still want to see it above.
All right,
Yeah,
so
where did
here's
you
the
see it
concern.
above?
The concern is not so much that it switches.
Yeah.
You see, switching will have an effect on lots of things.
Yeah,
Birds,
yeah.
migratory animals. If this switched quickly, let's say, migratory animals would have an issue. But let's assume they could figure that out. I don't know.
Oh,
But
that'd be a cool
if
place
it
for
actually, in the process of switching, if it goes down to almost 0 magnitude and then comes back together, the issue there is that this field then around the Earth essentially goes away, which means the means of redirecting these high energy charged particles goes away. And that could be an issue. That could be a big issue for the health of life on Earth. How much time we got left? Doesn't say?
Like a minute, I
Oh,
think.
that's it? Of camera time?
Mhm.
All right, that's perfect.